Hello, I'm Franklin Bauer from KREATiS. In this presentation, I will talk about the MechoA profiler that has been integrated in the OECD QSAR Toolbox and explain what it can do for you. We will start with how to install the MechoA profiler as an add-in for the OECD QSAR Toolbox and a general presentation of the profiler, and then go into detailed use cases to concretely show you its functionalities. Finally, we will conclude with the pros and cons of this profiler. First, I explain briefly how to install the profiler. You open the OECD QSAR Toolbox and then click on Options. Then in the repository client, you will be able to see and download the available add-ins, including the MechoA profiler. Once installed, it will appear in the general mechanistic section of the profilers. KREATiS has developed the MechoA scheme back in 2018 as a structural alerts model to predict the molecular initiating events, MIE in short, and further key events in the frame of adverse outcome pathways. It is built on and applies to a wide range of species, chemical groups, and mechanisms. Since its original publication in 2018, it has been regularly updated and is now in its version 2.2. The purpose of this scheme is to reliably define categories of substances for the development of read-across approaches and QSARs for ecotoxicity endpoints, and to unify toxicology and ecotoxicology with a same language. To make it more accessible and easier to use, we have proposed to ECA to integrate the MechoA scheme as a profiler in the OECD QSAR Toolbox. This proposal has been welcomed by the QSAR Toolbox Management Group, and thus, after months of work, MechoA profiler is now available as a downloadable add-in to the QSAR Toolbox since October 2021. We are now in the process of updating it to its version 1.1 for better speed of execution. Before we go through some case studies, I'd like to give you an overview of the categories that can be predicted by the MechoA scheme. You can find details on each MechoA class using the MechoApedia at the address shown on the screen. Rapidly, if the substance is predicted having only a MechoA 1, it means that it is not expected to have any significant reactivity or specific interaction with biological material. It just causes non-specific destabilization of cell membranes. If the profiled substance got a MechoA in the class 2 or 4, it predicts that this substance is metabolized quite efficiently and that the metabolites play a key role in the adverse outcome pathway, leading to an adverse effect. If the substance is predicted to have a MechoA 3, it means that the parent molecule is reactive and will regenerate adducts to protein and/or DNA in a non-specific manner. This is very useful for the prediction of skin sensitization, for instance, where this is the MIE. If a MechoA 5 or 6 is predicted, it is expected that the substance will specifically target and disrupt some key biological systems. Let's go for the first case study. Imagine we want to perform a profiling of a predefined list of compounds to identify any hazards before to use them experimentally. First, you input the structures, then you go to the profiling tab and select the MechoA profiler in the list at the bottom left of the window. Click on Apply and you will get the list of results in the table shown in 5. You can visualize the full MechoA prediction in the Windows 6, and you can even get more info on the underlying mechanism, including some literature references in the Windows 7. The example list shown here is comprised of 5 different phenol compounds. And actually, none of them behave the same, as you can see that they received a different MechoA prediction. This all depends on the nature and position of other functional groups on the phenol ring. As can be seen from the previous example, MechoA alone gives information that you could get only by running several other profilers. it is much more informative than most common classifications, such as Vera scheme, because it provides information on the species affected by each MechoA. It gives some basic information about the metabolism of substances and shows a specific text to explain the MechoA for each single prediction, which can give mechanistic clues to explain the MIE behind ecotoxicological effects, rather than just giving generic modes of action that other schemes often provide, which are not well defined in the AOP framework. Let's take another case study. Now we have one target substance, which is 2,4-dinitrophenol, and we want to build a category of similar structures, e.g. for a read-across purpose. To do this, go in the category definition tab. Here you can apply different strategies. You can use MechoA as first filter. This will take quite some time, but you will obtain in one step a homogeneous category only comprised of substances sharing the same MechoA. If needed, we can refine this category further using the subcategorize function, e.g. with structural similarity. Like this, we were able to restrict the category to 3 analogs in less than 1 minute. Another strategy is to go for a first grouping using structural similarity and then refine with MechoA as the subcategorized step. Using the atom-centered fragments fingerprint, I could get a list of 15 analogs in 1 minute only. Among these 15 closely related analogs, only 3 have the same MechoA as the target substance. The 3 analogs obtained here are the same as in first strategy, but the overall processing time is drastically different. We must recognize that MechoA is often not convenient to use in the subcategorized step, because the toolbox proposes only one automated selection of analogs, which is to remove all substances with predicted categories that differ from target substance. This is an issue because the MechoA scheme often predicts several categories per substance. E.g., a substance can have both MechoA 1.2 and MechoA 4.3. Therefore, it would be much easier if an automated selection by the toolbox could be keep all substances that are predicted with at least one category in common with targets. This is not only problematic with MechoA, but also with other multi-categories profilers, such as organic functional groups. Now, we actually want not just to have a list of analogs, but to fill a data gap using one or several analogs. Thus, we go in the data gap filling section of the toolbox to either perform a read across or a trend analysis, which is a simple linear regression QSAR. MechoA was used in the previous step to generate the category of 480 analogs for 2,4-dinitrophenol. So we have a homogeneous list in terms of mechanism of action. We can then use some physicochemical parameter as a descriptor to correlate with the toxic endpoint considered. The size of the list of analogs seems appropriate here. Otherwise, we could refine it further if needed. Let's say we want to predict the acute toxicity to fish, i.e. 96 hours LC50 for our target substance. In fact, in this example, there is some experimental value for this endpoint on the target substance, which is of 0.39 milligrams per liter. This value will allow us to evaluate the performance of different methodologies. We can try first the read across function. Among the 480 analogs, only 18 have data on this endpoint. In the graph below, you see the result of the read across using by default the predicted log KW as descriptor to quantify the distance between chemicals. Using this metric, only the 5 closest neighbors, highlighted in dark red, are used in a mean to generate the prediction for the target substance in bright red on the graph. The value obtained with this method is of nearly 7 milligrams per liter, so more than 10 times higher than the actual value. Now, we can do the same exercise with the trend analysis function, where we build some mini QSARs, if I can say. Using the default descriptor log KW, we get a similar prediction to the read across approach with 6 milligrams per liter. If we change the descriptor to molecular weight in the graph below, we also obtain a very similar outcome. Thus, we can infer that log KW or molecular weight are not relevant descriptors to model the toxicity of this group of substances. They are indeed oxidative phosphorylation uncouplers, i.e. MechoA 5.1, and their toxicity comes from their ability to transport protons across the inner mitochondrial membrane. Therefore, we have tried to use pKa as a descriptor instead. And this gives us this graph, which performs much better, predicting 0.72 milligrams per liter, thus accurately predicting the experimental value within a factor of 2. The MechoA details given along with the predictions of the profiler indeed explain how pKa and other parameters influence the activity of MechoA 5.1 substances. So thanks to the MechoA profiler, we were able to firstly generate a homogeneous category in terms of mechanisms of toxicity, and secondly, to select an appropriate descriptor for the quantification of the toxicity. Let us conclude here. The current version of the profiler available for download is the version 1.0, which works well, but it is quite slow. The version 1.1, which brings major speed improvement, has already been used in this work and is in the validation process with the QSAR Toolbox management group. MechoA profiler is not handy to use as subcategorized when there are multiple MechoA categories predicted for a substance, but is nevertheless good to build ecotoxicologically relevant categories for read-across and QSAR development. MechoA alone gives information that you could get only by running several other profilers and is much more informative than most common classifications. We are now in the process of the development of MechoA Plus in collaboration with Unilever and Liverpool John Moores University, the team of Mark Cronin, to complement current MechoA scheme with the numerous structural alerts developed by Sapunidou et al., which were published last year. At the end of the work, MechoA Plus will be integrated in the toolbox to replace and enhance the MechoA profiler. With this, I thank you for your attention, and we welcome your questions either online in the dedicated chat box or in person during the platform session on computational new approach methods.